So today we're looking at minimum spanning trees. So we saw yesterday that we could have some weights on the edges of our networks, which could mean like distance or they could mean cost. So now we're moving into these other things which will be to do with a weighted graph. So a tree is a connected graph that contains no cycles, multiple edges or loops. A tree may be part of a larger graph. So if you have a look here, I've drawn an example of a tree, and so you can see that they're all connected, but there's no loops. And to show you what a loop is, I've put them over here on the other side, so you can see you've got a loop in the green there. A cycle is when we go around to a certain vertices but end up, and then I've got multiple edges. So they are not, they're explaining what they are, but you can have a tree amongst a graph. So actually there in the blue, we could say that is a tree, that part there. I could even go out further and say that the highlighted bit there is a tree, as long as I don't connect up. So that's what they're saying what a tree is. So down here, we're going to talk about minimum spanning trees. So the rule connecting the number of edges of a graph to the number of vertices. A tree with n vertices must have one less number of edges. So if we have a look up here on our example up here, let's count the vertices. We've got 1, 2, 3, 4, 5, 6, 7, 8. We have 8 vertices. So what this rule is saying, we should have, so we're saying n is 8, so the tree should have 7 edges. So let's have a look. It's got 1, 2, 3, 4, 5, 6, 7, and it does. So there are the edges. All right. So not every connected graph contains it can have one or more trees in there. So exactly, and it so you might see a different tree to someone else. So here in the blue down here is an example of a tree, and in the red is another example, and the purple is another, and there would be multiple combinations that you could have, as long as they don't link together. Okay, so it's sort of like branches out like a tree. So a spanning tree is a tree that connects all the vertices, so in a connected graph. So that's what a spanning tree is. So we have to click out to all the vertices. So if we I might do it in green. If we have a look here, let's try. So say we start here, we want to branch out to all the vertices without connecting to, or looping in here. So I can go like that. I haven't connected. There you go. So what my there in the green, I haven't looped or connected back to each other, but I have gone to every vertex. Okay, so that is example of a spanning tree. A minimum spanning tree is when you use the minimum amount of length and you branch out to all the vertices in the graph. So if you have a look down here, we had this connected network down here, and we want to get a minimum spanning tree. So say we've started here at the 5, and we've branched along there to this vertex, and then we branched down to 4, we went out to 2. Now I don't want to connect them, so I might branch out somewhere else, which I did like that. I went out to 3 and out to 5. So you can see I've made it to every vertex, but I haven't connected up. So it's a branching out tree. Now the minimum is you want to do that in the smallest distance. So if you have a look, if we went, you can see there, I've actually got all the smallest possible distances getting out, because these were just 1. That's why we used that one and we added all them up and we got the minimum amount of units. So there's a little technique that you can use to work these minimum spanning trees out. And let's on this next problem. It's called Prim's algorithm. It's just like when you follow a step or a method, they'll call it like an algorithm. So what it says to do, it says choose a starting vertex and it can be any. So I'm going to just pick A. It says inspect the edges from this vertex and choose the one with the lowest weight. If they have the same weight, the choice doesn't matter which one you pick, and you know you have 2 vertices and 1 edge. All right, so if I look out here, the possible combinations that I could go out, I could go 2, 5, and 6. So what's the smallest edge coming out of A is the 2. So I'm going to follow that is the edge I'm going to pick. Okay, now I'm looking at out of B and A, so I'll just rub them out. So now we're looking at all the edges coming out of those 2. So that I have 6, I've got a 5, I've got a 6, and I've got an 8. So the smallest one out of all of those is this 5. So that's the one I'm going to pick. All right, so rubbing them out. And now I have D into the mix. So if you look at all the edges coming out of the vertex that we have at the moment, so we've got 3, 7, 6, this 6, we've got 8 and 6. Now, remember, we don't ever want to loop them back, so I'm going to get rid of that, because if I connect them, that would make a circuit, so I don't want to do that. So here, it's 3 looks like the smallest edge, so I will go out to here. So I'm at most of them. So really I want to connect, I'm trying to do a minimum spanning tree, which means I want to get to all of the vertex at the smallest. So now I'm probably looking over to get to D, to get to E and F, because they're the ones I haven't covered yet. So let's rub out those options. So if we look at our options to get to those ones, we've got a 5 here, we could take a 6, or we could take a 7. So because 5 is the smallest, I'm going to pick that one. Okay, and then if you look at what's left, I have this, I need to get to F, that's the only one I haven't got to, so I'll pick this method and it's 2. So if I drew this out, you'll see that it looks like it's a tree, a minimum spanning tree, but it's not connected in any way, like it's just branching out. So we went to C, goes down to E, and down to F. Okay, so then if I put all the numbers in, all the weights, and 2, and if I added all of them up, that will result in the minimum spanning tree weight. So we've got 2 plus 5 plus 3 plus 5 plus 2. So we end up with 17 would be the minimum amount of spanning tree.